Okay, in this section we're going to be going through 5D, which is the conservation of energy. We're also going to be going through 5E, which is using the conservation of energy to solve actual problems. So the first idea when we're thinking about the concept of conservation of energy is conserved. So what does that mean, energy is conserved? Conserved. That means that it can't be created. It also can't be destroyed. It can only be transferred into or out of a system. Meaning that a system being like an object or a group of objects. So if you have an object, energy might go in, energy might go out, but that energy has to be somewhere. It can't get destroyed and it cannot get created either. So that idea that all energy has to be somewhere is kind of mathematically explained in this conservation of energy equation. So if you look at it, there's a lot of terms, but basically what it's doing is it's describing what's happening initially to an object before some transformation happens to it, and then finally what happens to the object when after some type of energy transformation happens to it. For example, if you have a ball on the top of a hill, initially it's going to have certain types of energy, so at the top of the slope, and then finally once it starts moving at the bottom, it's going to have different types of energy. But it's basically saying this equation that it doesn't matter initially, where it starts, the final point where it ends, that energy went somewhere. It was converted from one form maybe into another, but that energy is always still there. It didn't go away. The first time you see W, that's work. That's energy that's transferred into or out of the system from like an outside area. For now, for sections 4E and 4D, we're going to say that's 0. So we're just going to cross that out for now. Later, that's not going to be the case. There might be some external transfer of energy, but for now, it's going to be 0. The next term is Ki. So what Ki is, if we think about remember K is the kinetic energy, Ki is going to be the initial kinetic energy of a system. So it's all the kinetic energy before some energy transformation, before something happened to it. So if the ball with the slope example, Ki would be, okay, is there kinetic energy on the top of the slope? The next term is Ui, so that's going to be the potential energy, the initial potential energy to be more specific, the initial potential energy. So that's the sum of all types of potential energy before the transformation, some type of transformation. So if we're thinking about that ball example, Ui would be up here. What are the types of potential energy initially? And this is kind of something that's important. So Ui, there's only really one type of kinetic energy. There's multiple types of potential. Right? There could be Ug for gravitational, or Ue for elastic, or Uc for chemical. There are many different types of potential energy, and Ui is basically including all of those. So if you had multiple, you would just add them up, and that would count as your Ui. The next term is Kf, so that is the final kinetic energy. So that's the kinetic energy after some transformation happened to it. So Kf would be down here with this ball example. So is there kinetic energy after that transformation, after it fell down the slope? And then you might have guessed Uf, that is the final potential energy. So that is all the types of potential energy, or the sum of all the types of potential energy at the bottom. It doesn't have to be the bottom of the slope, but after some transformation happened to it. In this case, it would be the bottom of the slope. So again, a lot of terms going on here, but really what it's saying is all the energy at some initial point in a system is equal to all the types of energy at the final point of some system. It's basically saying that energy might get converted to different forms, but it's always there. You cannot destroy it. So that is the first section. So now we're going to look at some kind of steps to take when you're solving out problems with this. So with 5E, we're going to get into, again, a little bit more how to solve problems with what we just talked about. So when you're solving a conservation of energy problem, it's important to use the following strategies. So the first one, your knowns and unknowns, that's pretty common, just writing out, what do you know? Do you know your mass or acceleration or initial velocity? What do you know? And then what are you looking for? Maybe it's your final velocity. The next thing, drawing a picture. I actually already have one drawn here. So drawing a picture of physically what's happening if there's not one given to you in the problem. The next one, it's a good, that's kind of going to be a little specific to energy, is you got to pick an initial point in time. So a point in time before some energy transformation happens. So if we had this case where we have like a block up here, and then it falls down, right, it'd be moving at the bottom. Right, if you wanted to pick an initial point, a good initial point might be up here before anything happens to it. I for initial. And then you got to also determine a good final point. So a good point after some energy transformation happens to it. In this case, it would be falling down that slope would be the transformation. So a good final point would probably be at the bottom right here. So before this should say after. So it should be a final point in time after the energy transformations. So after the energy transformation takes place. So this would be it right here. So this would be the final point in time. So again, that's important to pick both your initial and final points when you're examining the energy of an object. The next thing would be to take the conservation of energy equation and then cut it down to what types of energy are present. So again, if you think about it, certain types of energy might be present in certain spots, and you need to take that into account. For this example right here, there would be some UG at the top, because it's raised off the ground, and there'd be some kinetic at the bottom, and that's really it. There wouldn't be, there's no potential elastic energy. There's no potential chemical energy. So you got to simplify the equation down to just what's there, and we'll see that in a second. And then the last part is plugging everything into your equation and solving. So the very last part, let's see out a problem with this. So this is a conservation of energy problem. You may be able to solve this to work your way through. It's fine if you can't, but at the very least, make sure you have a setup, right? At the very least, you should be able to get your knowns, unknown, picture, maybe your starting conservation of energy equation. So please do that. Don't just have nothing. Okay, so I'll go over it. Again, make sure you have something down to start. So we have a 3 kilogram box is sitting at the top of a ramp. 3 kilogram box, top of ramp. That is 2 meters tall. The ramp is frictionless. And then behind the box there's a spring that stores 100 joules of energy, and that spring pushes the box down the ramp. And it's saying how fast will it be moving at the bottom. So I'm actually going to go a little bit out of order. I'm going to draw the picture first, because I think that's kind of helpful. So we have a slope. We have a box. It's up here. There's a spring behind it. That spring is pushing the box down, and then, right, we can imagine that box is going to be moving when it hits the bottom. Because it's falling, it's also being pushed by the spring. So our knowns, let's write that out next. Our known, we have a mass, 3 kilograms. We have a height, which is 2 meters tall. We have, this is a little tricky, the 100 joules of energy, that's really a potential elastic energy. So that's the potential energy stored in the spring. That would be 100 joules. And how fast is it moving at the bottom? That's technically VF. So again, not too bad so far, just knowns, unknowns in the picture. The next thing is to write out the conservation of energy equation. So all of the terms right here, kf plus uf. And the way we're going to do this is just simplify it down to make it a little simpler, because all these terms aren't going to be present. So good, the initial point's probably right here at the top of the slope. And then the final point's probably down here, the bottom of the slope, where we're trying to find the velocity there. So initial, final point. Initially, there's no work. We're going to say work's just 0 for now. And initially, it's not moving, so there's no kinetic energy at the top of the slope. But there is potential. There's actually two types of potential. There's UG, because it's raised off the ground, G. And then there is also UE, elastic potential energy, which is the energy that is stored in the spring. And then on the right side, we're going to look at what types of energy are present. There's no potential at the end because it's not raised off the ground. There's no chemicals. There's no more compressed spring. But there is going to be kinetic energy. So the last thing is we know UE, and we don't know these directly, but we know an equation for them from the previous unit, or not unit, previous section. So we know UG is mgh plus UE is equal to 1/2 mv squared. So we're just plugging in, so we know the mass, we know G, we know H, and then we're going to do plus UE, which is 100, and we get 1/2 the mass times v squared. And what we're going to do is we're going to simplify that down. I'm skipping a couple algebra steps in here, but if you're careful going through, you'll get at the velocity. And the velocity, the final velocity technically, is going to be, what, 10.3 meters per second. Get that circle right. It's better. Okay. So again, a lot going on here, but it becomes a lot easier if you're careful with your setup, your picture, your knowns and unknowns, your equation. So again, make sure you have this problem solution copied down and make sure you have the notes, and that is it for now.